Okay, Assalamualaikum and very good morning. Okay, due to COVID-19 announcement by the VC, so we have to do the class online. Okay, as requested by the USM itself. So for the vibration part, for the today lecture is lecture number 7. Okay, which is on the single degree of freedom, 2 degree of freedom system, which is force vibrations. Okay, and actually we have another 3 lectures remaining. Okay, which is next lecture is on the dynamic vibration absorber. Okay, where you will assign as a project 1, a group project, and you assign online and you have to submit also by email. And another thing is next week we cover on the last lecture, which is on the research opportunity on the vibrations part, and also the some revision of all the syllabus that we have learned. Okay, so for the project implementations, okay, you have to work in group, okay, within these 2 weeks, and finally we will have our test, okay, which is we will inform later the method of online test. Okay, so okay, for today we cover on two topics on the 2 degree of freedom, force vibration, and also the how you can do the transfer function for the 2 degree of freedom system. Okay, that will help you for your assignment also. Okay, this is the general 2 degree of freedom system, which is the force vibrations. Okay, so actually as you can see, it's actually the almost similar to the free vibrations, but in this case it have the excitation force here. Okay, at the M1 location. Okay, it can be both F1 at M1 location or F2 at the M2 location, and also it can be also at the one there's no force at the M1 location, or is also the force at F2 for the M2 location. Okay, so for this one, okay, actually you can see the first step is also, as general you have to develop the equation of motion. Okay, and this is generally the same one as you can refer back to your lecture notes for the free vibration. The difference is just this one, okay, this part where we have the force F1 here at the location of M1. Okay, so for this lecture maybe I can also draw you some, okay, for you to get more understanding on these topics. Okay, so basically we have the mass M2 here. Sorry for the handwriting because it's quite difficult to draw directly at the laptop, but however I will try my best to draw it for you. Okay, we have the M2 and also the X2, and M1 and also the X1. Okay, response number 1 and also the response number 2. So this one we have the stiffness K1 and K2, and at this one we have the force F1. Okay, where the total F here equal to MA or MX double dot. Okay, and as usual, what you have to do, you can separate it into these two. So this one, what you have in the upper part, so there is no connection here. It's only connection at the lower part. So for the upper part as a plus and below part as a minus. So for the minus we have K2, so X2 minus X1. And for this part also, for the plus minus the plus part, we have the K2. X2 minus X1, and for the below part we have k1, okay, is basically x1 minus 0, so that we don't include this 0 part. Okay. Okay, so next we can make it as an arrangement, okay, to this, okay, where we have a total f equal to ma, okay. So for the first part, okay, we have the total f of for this part we have a, for the m2 part, okay, we only have a minus k2 x2 minus x1, okay, okay, there is no plus part, okay, and it's directly equal to m2 x2 double dot, okay, correct. So this next one for the m1 part, okay, we have a force, okay, this f1 sine omega t, okay, for the force, the plus one, okay, and also plus one we have the force from the stiffness k2 k2 x2 minus x1, okay, and minus k1 x1 equal to m1 x1 double dot, okay. So by this, when you arrange, okay, as usual, the rule of thumb, you must arrange by expressions, okay, x double dot to x dot to x, okay, and arrange it by number 1, 2 or 3, okay, and then 3, yeah, okay, so that you can get the like this, okay, where you arrange and then you can arrange in metric form like this, okay, okay, for this equation of motion, okay. So for next, okay, okay, so we know that there will be a particular solution, okay, satisfied right hand side is not equal to 0, which is for the steady state solution. You can refer back your lecture notes on the 1 degree of freedom force vibration, okay, there's explained detail on this, and a homogeneous solution that satisfied right hand side is equal to 0. Okay, so the total response for the force vibration is equal to, okay, the homogeneous one, okay, mean the under dampened vibration plus the we have here is the particular solution is steady state. So what we are looking forward for this lecture is on the steady state solution. Okay, let's look at the particular solution, a steady state. Since the right hand side is sine, okay, let's assume we have the trial function like this, okay, where we have the x1 equal to amplitude x1 sine omega t and x2 equal to x2 sine omega t. Okay, so please be alert that the sine is always referred to the force. Okay, so this lecture is given by sine force, so the trial function is also sine, so that we can, when we do a derivation later, we can cancel out the sine. Okay. Okay, so when we substitute the equation into this equation of motion, we can get in this form. Okay, okay, we can get in this form. Okay, when you replace it as a k1, k11. Okay, actually in this k11, okay, in detail form, I can show you that. Okay, so maybe I can okay, maybe I can erase this first. Okay, or I can write down in the below part. Okay, okay, basically this is the part of k11. Okay, this is actually equal to k1 plus k2. Okay, k12 is equal to minus k2, okay, and K22 is actually equal to K2. Okay, so this is basically the detail form. Okay, this is one the simplified one. Okay, this is the detail one. Okay, okay, so when we go back to the lectures, sorry, okay, so actually this K11 is referred to K1 plus K2. Okay, and also this K12 is referred to minus K2, and K22 is for the K2. Okay, so you can uh, derive it, okay, and then you can get in terms of this form. Okay, basically, okay, when you include all the uh, okay, the trial function, okay, which basically before this the trial function that we have this one, okay, we convert you differentiate it to get in terms of expression, okay, and then you can replace to the previous equations, okay, here x1 double dot and x2 double dot and x1 dot x1 and x2, okay, so later you will get the final form like this. Okay, so actually this is the same as the equation number 50 in the 2 degree of freedom free vibrations, okay, but this have the f1, so you can you notice that there is no sign here because we can cancel out the sign on the right hand side and the left hand side. So that's why I said before that you must include the same excitation, I mean the same trial function for the uh, excitation, okay, the response based on the excitation force. Okay, so basically when you get into like this form, actually you can transfer it into the impedance metric. Okay, so because we will want to move this metric to the right hand side so that we will able to calculate the x1 and x2. Okay, okay, so uh, always remember that when it comes to the force, we always want to determine the response of the system. Okay, it's the same case when you go to back to the your uh, the force for the first degree of freedom is the same that we for it when it comes to the force vibration, when excitation force, we always want to determine the response. Okay, so okay, so when we move this metric, okay, sorry, when we move this metric to right hand side, so it become an inverse metric. Okay, so for the left hand side is remain as x1 and x2, so the impedance metric is become inverse. Okay, it's a quick metric review for the inverse of 2 multiplied by 2 matrix. Okay, where we have a, b and c, d here. Okay, so when inverse, okay, we assume that we have this equation, okay, 1 minus AD, okay, AD 1 sorry 1 divided by AD minus BC, okay, and we have this metric where we change the location of AD, okay, and we minus B and C. Okay, this is you have learned before also in calculus and mathematics uh, subjects basically. Okay, so the next one, okay, we have to solve it lah. Okay, so this is the what we I have write to you in terms of simplified form where we can replace this a d a b and a b and c d like this to represent our detail matrix. Okay, so what we have is a actually is equal to z11. Okay, so z11, okay, is actually equal to k11 minus m1 omega 2. Okay, when we refer back to this one, actually this is z11 location. Okay, and then Z12 is minus K12, okay, ni 12, okay, minus K12. So this one Z12 minus K12, and finally Z22 is K22 minus M2 omega 2, okay. So this is the one for the Z22, okay. Okay, from that, when we replace the K11, which is equal to K1 plus K2, and K12 is minus K2, and K22 is K2, okay, based on the model, and then later we can solve this equation lah, okay. Okay, so if the, okay, if you solve it, okay, so this one, okay, you can solve it, okay. Okay, so you already have this, okay, detail, and this part is multiplied by this f1, so z22 multiplied by f1 here, so minus z12, okay, multiplied by 0, so this we can slash out, okay, the below part is remain like this, okay. Also for the below part, okay, you can minus z12 multiplied by f1, okay, here, and plus, here plus here, z11 multiplied by 0, okay. So finally you will get in this form x1 and x2, okay. Substitute the x1 and x2 value to this trial function, so you will get in terms of response, okay. So to complete solution, you can find that the omega is actually the excitation force of positive frequency lah. So when the m1, k1, m2, k2, and also the omega is given, so you can have a solution, okay. Okay, so I want to highlight this the differences between the free and the forced vibration. Okay, actually, the free, what is different? Okay, for the free vibration, okay, we found the first step is to find the equation of motion. Okay, okay, in terms of this metric, and then we get into of this what call it trial function. Okay, sorry. And then for the natural frequency, we determine the natural frequency, and then later we replace the natural frequency to the equation motion, and then we can get in terms of mode shapes. Okay, okay, this is equal to 0. Okay, where we can find that lah. But for the force vibration is we find in the steady state solution, where in terms of harmonic forcing, okay, we can find the equation of motion. Okay, similar to this, the difference is just for the force. Okay, and then we replace the trial function is must be the same, is a sine. For the force, it must be sine. If given the force is cos, and it must be cos. Okay, so when the given the m, k, and omega is given, okay, so that we can determine the response in terms of magnitude. Okay, okay, so this is another example. Okay, okay, so find the steady state response of the spring mass system. Okay, find the steady state response of the system in figure here. Okay, when the mass m1 is excited by the force f1. Okay, so f1 is equal to f10 cos omega t. Okay, so for the solution, okay, so we derive the equation as usual. Okay, so please be alert, this is a 2 mass and 3 stiffness. Okay, I have shown you before how to get this equation of motion, because this is have the additional of k3 here. So please make sure that you alert is have the additional of another k here. Okay, so when you compare back to previous equation, okay, so k1, k11, k12, k12, k22. Okay, so when I go back to here, okay, so this is the previous one. Okay, when you have a k1 at this location is k1 plus k2. Okay, minus k, you have minus k2, k2 here. Okay, and for this 2k actually is a k2 plus k3. it also have 2k here instead of just a 1k. Okay, so because there's a k3 here. Okay, so that's the thing that you have to alert. Okay, so from this, then another thing that the force is given by cosines. Okay, so that you must have a trial function of cosine. Okay, so the trial function will follow the given excitation frequency. Okay, so for this one, the m11 is equal to m22 is equal to m. Let's assume that n1, okay, here, okay, you can assume that m1 m equal to m1 equal to m2, k equal to k1 equal to k2 and equal to k3 lah. So for this case, they assume that all the values is given is the same, so that it is simplify like this lah, mm to k and to k like this. If not, then you should be m1 and m2, okay, k1 plus k2, k2 plus k3 and so on. Okay, so later, okay, when you come to the solution, you will get like this. Okay, okay, it's a similar one as what you have uh, here, what you have uh, shown before here. Okay, but the same method is can be used. Okay, and you can get in this final form lah. Okay, so from this, when the question is given like this, if the mass is equal to 2 kg, stiffness equal to k Newton per meter, force F10 equal to 4 Newton, under the excitation frequency of 30 Hz, what is the resulting displacement of x1 and x2 for the 2D freedom system? So M, K, F, and omega is given. So you have the omega value, M value, K value, and F value, so that you can solve the x1 and x2. Okay, so later you can try it by yourself and get the result. It's just a straightforward replacement value, and then you can get the value of x1 and x2, and later you replace back with this to this equations, the trial function, and then you can get in terms of displacement. Okay, this is only amplitude. Okay, please be alert, the bigger x is the amplitude. But in terms of if this question asked about in terms of response, displacement, you must show in terms of this form. Okay, the next one is on the transfer function. Okay, this is the mostly related to your assignment. Okay, so you can use this as a reference on how you can derive your equation of motion. Okay, and also later you can build up your model in the MATLAB and simulating software. Okay, for the two-degree of freedom system as shown in the figure, determine the output input relationship of the system in terms of transfer function. Okay, so now for the system, okay, you can show the m1 here, the plus and minus, m2 plus and minus. Okay, in the plus direction, so now you have a c, okay, x 2 minus x1 double dots k2 connection at this location. Okay, and then at the below part you have a minus, okay, c1 and k1. Okay, and also you have the two excitation force here. Okay, so you also have the excitation force in plus direction. Okay, same goes to the m2. Okay, you have the k3 and c3 here at the plus location, and at the minus location you have a K2 and C2, they connected here in the below part. And for the plus also for the M2 you have the F2. Okay, so the rule of thumb to solve this is you must derive the equation of motion first. Okay, so and then you go to the Laplace transform, Cramer's method, and finally you can get the transfer function. So this is when you arrange equation of motion, this is what you get. Okay, what I have still tell you before, you must arrange by the acceleration first. Okay, x1, okay, and then at x1 double dots velocity, you can see here is arranged first 1 and second 2. Okay, x dot 1 and x dot 2, and finally displacement, okay, x1 and x2. Okay, same goes to the second for the mass number 2. Okay, you have the mx2 double dot for the acceleration, x2 displacement, okay, velocity. Okay, and finally you will get of displacement. So from this you can transform into a Laplace transform. Okay, you replace the trial function here. Okay, and finally you can rearrange. Okay, so that you can transform into a like this. Okay, so for the x1, okay, this is for the x1 and this is for the x2. Okay, you can refer back to here. Okay, this is for the x1 and also x1 here. Okay, you must arrange it upper and below, and for the x2 here you must arrange it like this. Okay, so this is the Cramer's method. Okay, you can search and find how you can solve in terms of Cramer's method to get in terms of transfer function form. Okay, so for the below parts, okay, this is the ds value. Okay, you can solve it in terms of like this. Okay, and for the upper part, okay, d1 and d2, where you replace the f1 f2 here for the d number 1, this part is remain at above, and then you can solve it. Also the same one as the d2, where you replace at this number 2 locations. Okay, and this one is remain here. Okay, so let's say as your assignment, either f1 or f2 will have the value and another one will be 0, so you have a more simplified formula. Okay, so that you can solve it. Okay, so that's all for today lectures. I hope you can understand a little bit. It's almost the same as the free vibration, okay, but it have an additional of a excitation force, okay. So that's all. If you have any question, maybe you can ask later in the e-learning websites. Okay, sorry for any inconvenience. I hope I will have tried my best to explain you in terms of this video form. Okay, so thank you very much. Enjoy your class.